Hi. Now I'm the 15 minutes between you and your lunch. I'm sorry for that. Please bear with me. My name is Wera. I'm a PhD student at the University of Hohenheim and a quantitative genetics scientist at KWS in Germany. And I would like to present two ideas to you how to guide a DL model towards G/E prediction. So the results I'm going to present were derived from a hybrid dry grain yield dataset sampled across major European growing areas with 23K observations in total from 170 locations about, and collected across 12 years for about 220 genotypes. As predictors, we used environmental data, both weather data and soil. We had information on a management variable, so either the trial was intensively or extensively treated, and the name of the country, obviously. Now, this is how the data set looks like if you decompose it into its sources of variance. What you see circled in red are the 12% related to the genotype, so the 12% of variance related to the genotype and its interactions with the environment. If you look to the right, then the zoom in shows you that about or a bit more than 50% is attributed to the genotype main effect, and the remaining part is associated to the interactions with the environment. Now let's look back to the left side again. Actually, around 88%, so the vast majority is not attributed to genotype, it's attributed to environmental main effects and their interaction. And now I would like you to keep this in mind because it will make it pretty obvious that if you fit or if you want to train a model which is not a linear mixed model or a Bayesian model where you can formulate dedicated model terms that allow you to, for instance, focus on G/E. If you, for example, use a deep learning model, then you might end up in a situation where your model will become very good at predicting what is the major driver of your response variable. And if that's yield, like in this case, then this might be your environmental main effects and their interactions, rather what you might be interested in as a breeder. So the question is how to tell your model, no, I don't want you to tell me which environment is the most fertile. I want you to tell me where to grow which genotype. And so actually, what we want to predict then is probably not yield per se. Probably what we want to predict is rather the difference between yields of genotype within environments. Now, with exactly this thinking in mind, we developed two different ideas, and I would like to start with the right-hand side, designing target variables for deep learning models. And what I'm showing here is basically you would use a linear mixed model, decompose it into its sources of variance, just like I had shown in the plot before, and then you extract the estimated effects coefficients, and you form a linear combination of everything that is associated to your genotype. And we have two different types of it here. So in green, you see the y hat GE, which is the sum of all the genotype times environment interaction effects. And in red, you see the y hat GGE, which additionally will include the genotype main effect. And now this is what you're going to supply as a target variable to your deep learning model instead of yield per se. Now let's have a look at the left-hand side again. This approach is trying to answer exactly the same question, but coming from a very different angle. Now we again supply yield per se as the response variable to our deep learning model. But what we're changing now is the optimization function the optimization engine basically of our deep learning model. So the default in a DL or ML model would probably the mean squared error of the mean squared error or the mean absolute error. And what that means is that you would optimize, or your model would optimize for minimizing the residual between the true and predicted yield observation. But if you remind yourself and you look at this plot of the variance components again, then it will become obvious to you that the main driver, or what dominates that residual, will be very likely the environmental main effects and their interactions, and not the G. Now, our idea was to replace exactly this loss function with something like the mean squared error of a difference between genotypes within an environment. So we heard this metric a couple of times this conference already. It's used a lot for model evaluation. We're basically taking it and moving it one step ahead into the model optimization process. And what it is doing is it's basically the difference that we're making here is that now we're minimizing the residual of the true and the predicted pairwise differences between genotypes within the same environment. And exactly this change allows us to basically factor out the environmental main effects and their interactions, and again focus only on the red circled box. Okay, so how does this in the end affect our results? What I'm showing here is results from leave one location out cross-validation from exactly the data set I presented in the beginning for both the design target variable and the MSED loss function approach in green and in pink. And on the y-axis, you see the Pearson correlation coefficient. On the x-axis, you see the type of model, so the target variable we used to train the model on, and then the name of the model, and you see 3 different benchmarks. You have in gray the genotype main effect. So this is what we estimated in each CV split from the training data set, which is kind of the lower benchmark. Then in cream, we have a linear mixed model trained on GDY. Basically, this is the E-kinship, environmental kinship model as proposed in 2014 by Hakin. And then in red, our last benchmark would be a deep neural network trained on GDY without altering the loss function or anything as a baseline, basically. So what I want to show you is that if you make the comparison, you see that our design target variables could deliver a plus 12 PCC point advantage and the loss function approach a plus 10 PCC point advantage over a baseline deep neural network without any guidance towards predicting G by E. And if you compare it to the genotype main effect itself, then you see that those two approaches deliver a 5 and a 4 PCC point surplus over the genotype main effect, meaning it's actually making sense to model G by E. And we're better off doing this than assuming a constant ranking of genotypes across sites and years. And last but not least, we could show that the target variable approach performs slightly better, so plus 2 PCC points over the classical E-kinship model, and the loss function approach performs just as well. By now I should have been clear enough on stating that it is important that if you are thinking of using a deep learning model or a machine learning model, that you are aware of what you want to optimize for. And if that is G times E, then probably you need to think of ways how to factor out your environmental main effects. And the question still is, so what to choose of the two methods that I proposed, target variable design or loss function. So we saw that both perform pretty similar, not only in the CV scheme that I showed you, but also in the 3 other main scenarios that we tested. Both methods perform either equally well or slightly better than the kinship-based regression model suggested by Hakim. I would say only from a workflow perspective, I would prefer the loss function approach, simply because it does not require you to prefit a linear mixed model and design a response variable. It's a simple one-stage approach where the only thing you need to do is tweak your loss function engine or your optimization engine, basically. Now with that, I'm on my last slide, and this is more like an outlook and a reminder on why we are doing all this. So the methodology I presented can serve as a backbone for simulation platforms. For G/E, you can simulate a portfolio of genotypes into your target population of environments. And this is exactly what I did here using the MSED loss function approach and a deep neural net, using a set of genotypes and looking retroprospectively. So each color is corresponding to a different genotype, and it shows you where the model predicted which genotype to be the number 1 at a given coordinate and year combination. Now, this has obviously very broad use cases in breeding, for instance, for candidate selection, but also if you look into portfolio management and product placement, or later on at the farm level variety recommendation. With that, I'm finishing with a quick advertisement on a public RAI data set that we have recently published with our KWS colleagues. It's from our KWS hybrid dry breeding program from GCA testing. And you can find it on the link I'm sharing here. And I would especially encourage that as a resource for teaching and as a toy or as an exercise data set, please approach us or me if you have questions. Thanks to everyone who was contributing to this work, my scientific supervisors, my colleagues from KWS, many of them are here in the room, and also obviously all the institutions that were involved in putting together this data set. So thanks for your attention.